All right. Hello and welcome to my YouTube channel, The Engineer Edge. In this video tutorial series and course, I'm going to teach you how to simulate the fiber reinforced concrete and abacus with various kinds of fibers, um, the lengths of the fibers variation, the um, percentage of fiber variation in all those steps, and I will also um, provide you a description to purchase uh, the model in a very reasonable price, and also I will teach you how you can simulate the fiber reinforced concrete and abacus. So these are the parts that you are watching right now. We have the cylinders, and we have the top plate and bottom plate. And um, if we go to assembly, we can kind of um, arrange them properly by first placing the bottom plate. The order doesn't matter here, but I'm just showing you how it can be done. Uh, This is one percentage of the fiber. This is the second percentage of the fiber. This is the third percentage of the fiber. And this is the complete cylinder. We can switch on the transparent view to see what's going on inside our model for the fibers. Also, we have this top plate here that's given over here. And just look at here that how the fibers are placed automatically by itself in this concrete cylinder here. So first we need to discuss the theory and equations and applications. And there are various kind of research and uh, experiments performed on the fiber reinforced concrete, in which one of them is the numerical simulation of fiber reinforced concrete under cyclic loading using extended finite image metal and concrete damage plasticity. So you can go to the theoretical background, you can search about this research article, and you can study how the fiber reinforced concrete theory, equations, and applications are found here. So let me introduce the fiber reinforced concrete. We need to discuss the definition and the history of the fiber reinforced concrete. Basically, fiber reinforced concrete is a composite material. It consists of concrete and discrete reinforcing bars. I just showed you here. These are the discrete bars, and these reinforcing bars are the fibers. Actually, they have a uniform length, and these fibers are uniformly distributed and randomly oriented with the concrete matrix. And in the assembly you can see this is the concrete matrix. I demonstrated how to do it, and the fibers that are uniformly distributed and randomly oriented within the concrete matrix are visible over here, right? And the concept of adding fibers to these materials such as concrete is basically to enhance their properties that has been around for centuries. However, the modern use of fibers in concrete started, and as per some literature, in 1960, um, initially with the use of steel fibers, and many research articles have quoted it here. So you can check it, you can study this paper, you can study similar research, just like the one that is mentioned here, and we need to find out the use of the fiber reinforced concrete to utilize them and the research that we are studying. So why there is a need of fiber reinforced concrete in this modern era. And before that, I mentioned the orientation of the fiber reinforced concrete structures. So, um, why do we need to mention the fiber reinforced concrete orientation, right? So let's look at here. Look at this picture. We discussed something about the fiber orientation. That these are randomly oriented here in this fiber. So it's a very common phenomena, and the orientation affect the compressive behavior, tensile behavior, and flexural behavior of the FRC, and it has a very crucial effect on its mechanical properties in hardened state. For example, we have this concrete cylinder that is placed over here, right, in this manner. And let's say we are representing this concrete cylinder, and the fibers are placed in this manner over here in one direction. For example, if these are placed in one direction, so if I apply a load on it on top, the magnitude of P, right, to check its mechanical properties. Obviously, I'm going to check its stress strain curve to find out what's going on in this model. So I have to confirm that the fiber orientation that it's present here is going to cause a in this orientation is going to cause a failure, a crushing failure in this manner, right? And in similar manner, if the fibers that are present in it are oriented in this direction, then I'm going to obtain a, a complex failure mechanism here, right? If all the fibers are in this direction, right, then it's going to split in the middle here, right? So the fiber orientation, it significantly affect the mechanical properties of FRC because the orientation of the fibers influence how they carry and distribute loads within the composite materials, and there are some uh, impacts on the mechanical properties. So first, if we discuss the strength and stiffness, so we have two kind of fibers over here, and I was discussing this in a recent study as well. The first kind of fiber, the orientation is aligned fiber. The, the second one is the uh, randomly oriented fiber, and the third one is multi-directional alignment here, right? So let's say for the first cylinder that we are going to discuss over here, we have this kind of cylinder which is placed over here, and we are going to check what's going on in this model. So if the fibers are aligned in a single direction like this that are present in this model. So whenever I apply a load on it from the top, it's going to show me this behavior of the crack, like it will split in this way. When fibers are aligned in a direction of the applied load, they provide basically maximum strength and stiffness because the fiber efficiently carry load. But that's the case when you are using flexural loading. If you are using compressive loading, then that's not going to help you because of the tension and compression zone. If the fibers are oriented in the this manner, for example, this is the cylinder that is placed over here, right? And these fibers are uh, oriented in this manner, right? So overall in compression, it's going to give you a very best performance if the load is applied on it, and the cracks will be something like this randomly, but it will resist with a very high precision. So if the fibers are randomly oriented in compression, the strength and stiffness are generally higher because the load is distributed unevenly among fibers and they carry out the load. But if the flexural loading is applied, then this is going to not help you in the analysis and strength increase and enhancement. While for multidirectional alignment, in some applications, fibers are aligned in multi-directions to provide strength in more than one direction, which balances performance in multi-axial loading. So the the process that we are going to enhance in terms of the properties, we are basically discussing this. If you are getting this curve in terms of the stress strain of the response of this compressive loading, and these are aligned fibers, then this is a very less value. And if these are oriented, this is going to be a very high value. But if it is a flexural phenomena, it's going to be a different way. Regarding the impact on the toughness and resistance, so if the cross-linked fibers are oriented at angle of 45 degree, just like we are observing here, it can improve the toughness and impact resistance of the composite by enhancing its ability to absorb energy through quick deflection and bridging phenomena. And if the discontinuous fibers, randomly oriented discontinuous fibers, are incorporated, they can also enhance toughness by preventing catastrophic failure as they provide reinforcement in multiple directions, though less efficient than continuous aligned fiber in terms of flexural loading. While if we discuss the fatigue resistance, so the orientation of fibers affect how fatigue crack initiate and propagates, and it's align fibers in the load direction and improve fatigue resistance because they can reduce the likelihood of crack formation and growth along the fiber directions. We have also to include the thermal and chemical stability, although we are not considering them in this ABAQUS file that we are going to discuss here, right? But a fiber orientation also impacts the thermal and chemical stability. It aligns with the code, and it's basically reduced thermal expansion in specific direction, while random orientation may lead to more uniform property across composite, which is a good way to consider. And another thing is anisotropy. So FRC with aligned fiber exhibit anisotropic properties, which means that their mechanical behavior differs based on the direction of the application force. So this anisotropy must be considered in design as the material may perform exceptionally well in one direction but poorly in other direction if you are considering homogenization. So for homogenization techniques, you can study on the literature that how the homogenization is performed by some researchers to consider the fiber reinforced concrete model and analysis. But if I summarize this, the orientation of fibers in fiber reinforced composites play a crucial role in determining their mechanical properties such as strength, stiffness, toughness, fatigue resistance, and anisotropy. So you have your own choice. You can select whatever fiber direction you want to consider in your research study. So I have these parts that I have developed with script. You can look at here. We have these parts here, and we can see what's going on in this model. So next thing is, um, why do we need to consider the need of fiber reinforcement?